If you've listened to, well, basically anything that's ever come out of a speaker, you've heard dynamic range compression.
Oh,
Well,
absolutely.
a pop song, this deep dive, even one of those commercials that's way too loud. You've heard DRC.
It's everywhere. And it can sound super technical, but let's just cut right through that.
Please.
At its heart, compression is simple. It's just a process that makes loud sounds quieter and sometimes makes quiet sounds louder.
So it's squashing the difference between the loudest and quietest parts, compressing it.
That's it. You're compressing the dynamic range.
So our mission today is to get past the jargon. We want you to really understand the artistry here because every single knob you turn is a trade-off.
And these things, these compressors, they are in hardware racks, they're software plugins, in, every DOP. They're in live soundboards,
Everywhere.
everywhere. And let's make one key distinction right up front. Compression and limiting. They're the same process. A limiter is just a compressor on, let's say, beast mode.
A very aggressive compressor.
Exactly.
Okay, that's a great place to start. So let's build this from the ground up. I know there are two fundamental ways to do this.
Right. You've got downward and upward compression. They both get you to the same placeless dynamic range, but from totally opposite directions.
Let's do the common one first, downward compression. This is the one most people think of.
It's the workhorse. So with downward compression, you set a level the threshold. Anything that gets louder than that threshold gets turned down.
And anything below it?
Totally untouched.
Mm-hmm.
Stays exactly as it is. You're essentially pushing the ceiling down on the loud parts.
Got it. So the other way is upward compression.
Right. And this one does the opposite. It takes all the quiet sounds below the threshold and turns them up.
But it leaves the loud stuff alone.
Leaves it completely alone. So instead of lowering the ceiling, you're raising the floor.
Okay, wait. So if downward is for controlling peaks, why would I ever want to use upward compression? It seems like it would make things messier.
It's a great question. You wouldn't use it for peak control. Upward compression is all about subtle enhancement.
Like what?
Imagine you have a nice acoustic guitar recording, but the little details, the finger scrapes, the breathing, it's all getting lost. Upward compression can lift just those quiet moments up, making the whole performance feel more intimate without ever touching the loud strums. It's gentle.
Ah, so it's for detail, not for smashing things. That makes a lot more sense.
Exactly.
Okay, just to close this loop, what's the opposite of compression if I want more dynamic range?
That's called expansion. And the most common form, the most extreme one, is a noise gate.
A noise gate.
Yeah, that's applying something called downward expansion. It takes quiet sounds like, amp hiss or room noise, and it makes them even quieter. We're just silent.
Got it. Okay, before we get to the fun knobs, I'm curious about how these things are built. I hear the term sidechain all the time. What is that really?
So when a signal goes into a modern compressor, it splits in two.
Okay.
One copy goes straight to the part that actually turns the volume up or down the amplifier. The other copy goes to the measurement circuit. That's the sidechain.
So the sidechain is like the brain of the operation.
That's a perfect way to put it. It listens to the signal and tells the amplifier what to do.
And most plugins today use what's called a feed-forward design.
Yeah, feed forward. The sidechain measures the signal before it gets changed. Old analog gear sometimes used a feedback design, measuring after the change.
Does that make a difference?
A subtle one. Feed forward is cleaner, faster. Feedback can be a little grittier, more reactive. It's often that vintage character people are chasing.
That's a great bit of context. All right, let's do it. The four main controls. We have to start with the threshold, the starting line.
Is the line in the sand. A compressor does absolutely nothing until the signal crosses that threshold, which you set in decibels, or dB.
And here's the part that I think trips people up.
Yep.
A lower threshold means more compression, right?
Right, it's counterintuitive. If you set it really low, say minus 40 dB, then almost the entire signal is above that line.
So the compressor is always working.
Always working, hard. A high threshold, like minus 5 dB, means you're just catching the very, very loudest peaks, much less compression overall.
Okay, so once the signal crosses that line, we need to tell it how much to turn down. And that's the ratio.
The ratio, yep. This determines the amount of gain reduction. The classic example is always 4:1.
Let's break that down.
A 4:1 ratio means for every 4 decibels, the signal goes over the threshold.
The compressor only lets 1 decibel out.
Exactly. It knocked off 3 dB of that peak. The output is only 25% of what went over the line.
It's all about how hard you want to clamp down.
That's the math. But now we need to talk about time. And this, for me, is where the real artistry comes in. Attack and release.
This is what gives it the character. So attack first.
Attack is how long it takes for the compressor to apply that full gain reduction, once the signal crosses the threshold. It's usually measured in milliseconds.
So a fast attack means it clamps down instantly.
Instantly. Which can sound very controlled, but sometimes a bit dull. A slow attack, say 50 milliseconds, is interesting. It lets the initial punch of the sound through.
The transient.
The transient, yes.
Oh,
Like the crack of a snare or the pluck of a guitar string.
Yeah.
It lets it get through before it turns the volume down. That's how you make things sound punchy.
So for a big, punchy drum sound, I'd want a slower attack. Let the initial hit through, then compress the body of the sound.
You've got it. Then there's the release.
Which is how long it takes to let go.
Right, how long it takes for the gain to return to normal after the signal drops back below the threshold. If it's too short, you can get this weird pumping sound or even distortion.
And if it's too long?
The whole track can feel squashed and lifeless because the compressor never really gets a chance to recover before the next hit. You really have to time the release to the rhythm of the song.
And the craziest part, which you mentioned, is that there's no industry standard for these times.
None. A 10-millisecond attack on one compressor might behave totally differently from 10 milliseconds on another. You just have to use your ears.
Always use your ears. Okay, let's talk about some of the refinements, how the compressor feels when it kicks in. Soft versus hard knee.
The knee is just the shape of the response curve, right at the threshold. A hard knee is exactly what it sounds like. It's a sharp corner. The moment the signal hits the threshold, bam, full compression.
Abrupt. Good for things like drums, I imagine.
Perfect for drums. When you want that immediate tight control, a soft knee is more gentle. It starts to apply a little bit of compression before this signal even hits the threshold.
It eases into it.
It eases in, gradually increasing the ratio. It makes the whole process way less obvious.
Yeah.
It's much more transparent, which is why you'd use it on vocals or piano or across a whole mix and mastering.
Yeah, and how does the compressor even know what the level is? How is it listening? That's peak versus RMS, right?
Right. A peak sensing compressor responds to the absolute highest, fastest spike in the waveform. Instantaneous level.
So it's great for catching those really sharp, quick sounds.
Exactly. It's what you need for safety limiting, to make sure nothing ever clips. But our ears don't really hear those instantaneous peaks as loudness.
That's where RMS comes in.
Correct. RMS stands for root mean square. It's basically an averaging function over a short period of time.
So it's closer to how we perceive loudness.
Much closer. An RMS compressor reacts to the overall energy and density of the sound, not just one sharp spike. It gives you that more relaxed glue kind of compression.
Okay, so since we're turning down the loud parts with downward compression, the whole thing is quieter. We need to turn it back up.
And that's makeup gain. It's a simple volume knob at the end of the chain. You compress to control the dynamics, then you use makeup gain to bring the whole thing back up to a healthy level. It's essential.
Now for a cool digital trick, if I want a punchy sound, I need a slow attack. But that means the very first part of the transient gets through uncompressed. How do we fix that?
With a function called look ahead. It's really clever.
How does it work?
It delays the actual audio by just a few milliseconds. But the sidechain, the brain, gets the signal instantly with no delay.
So the compressor's brain sees the peak coming before the audio even arrives at the amplifier.
Precisely. So it has time to react. You can use a nice, slow musical attack time, but the compressor still catches that transient perfectly because it got a heads up.
The only trade-off is a little bit of latency.
A tiny bit of latency, yeah. But the control is incredible.
Okay, let's crank the intensity way up. Let's talk about the extreme end of this, limiting. Specifically, brick wall limiting.
So limiting is just compression with a really high ratio, think 10 to 1 or more, with a fast attack. A brick wall limiter takes that to the absolute limit.
Like infinity to 1.
Ratios of 20 to 1,
Yeah.
infinity to 1, yeah. And an almost instantaneous attack. Its only job is to be a ceiling that the signal can never pass. An impenetrable wall.
And this isn't just for music. This is a safety tool.
A critical one.
Yeah.
It's used in live sound and broadcasting to prevent clipping and protect equipment. Bass amps have them built in to stop you from blowing up your speakers with a loud pop.
This focus on making things as loud as possible led to the loudness war.
Ah, the loudness war, yes.
Yeah.
That was this period where engineers just kept pushing things louder and louder, using more and more compression and limiting.
Oh, so their song would sound louder than the next one on the radio?
And the result was just harsh, fatiguing music. When you slam a signal that hard against a brick wall limiter, all the punch, all the dynamics, all the life just gets sucked out of it.
We hear this in advertising, too. Why do TV commercials sound so much louder than the show?
It's because they're hyper-compressed. The peak level might be the same as the TV show, legally. But because it's so compressed, almost the entire commercial is sitting right at that maximum level.
So the average loudness is way higher.
Way higher. It's a trick to grab your attention.
Okay, let's move from safety and loudness wars to pure creativity, using that sidechain we talked about.
This is where it gets really fun. So sidechaining is just using one sound to control the compressor on another sound.
The classic example is ducking, right? Like with a DJ.
Exactly. You feed the DJ's microphone into the sidechain of the compressor on the music. Whenever the DJ talks, the music volume automatically ducks down. When they stop talking, it comes back up.
So simple, so effective. But modern music has taken this to a whole new level with rhythmic pumping.
Oh, yeah. That is the sound of modern EDM and hip-hop. You take a kick drum, and you feed that into the sidechain of the compressor on the bass line,
For everything.
or everything. So every single time that kick hits, the entire mix just dips in volume for a moment and then swells back. It creates that signature pulsating groove.
It's the sound of a genre built on a sidechain. You can also use it surgically for something like de-essing.
Yeah, that's a brilliant use case. You EQ the sidechain so it only listens for those harsh S's frequencies, usually around 4 to 8 kilohertz.
So the compressor only kicks in when the singer makes a loud sissus sound.
Right. And it only turns down those harsh frequencies without affecting the rest of the vocal. It's incredibly powerful for cleaning things up.
And engineers are always stacking these things in complex ways. What about parallel compression?
Parallel or New York compression. It's a fantastic technique. You split your signal, let's say drums, in two.
One clean, one compressed.
One is totally clean, uncompressed. The other you absolutely smash with a compressor. I mean, obliterate it.
And then you blend them.
Then you just blend a tiny bit of that smash signal back in with the clean one.
What does that do?
The smash signal brings up all the low-level detail. The room sound, the tail of the reverb, the ghost notes. You get all that energy and density, but you still have the punch and impact from the clean, uncompressed signal. It's the best of both worlds.
For even more control, there's multiband compression.
Multiband is like having several compressors in one. It splits the audio into different frequency bands, lows, mids, highs, and you can compress each one totally independently.
So I could tame a boomy bass guitar without affecting the cymbals.
Exactly. It's a mastering engineer's secret weapon. Or you can do serial compression.
Just two compressors in a row.
2 in a row. Maybe a gentle RMS one first to kind of glue everything together, followed by a super fast peak limiter just for safety. It can sound surprisingly transparent.
And we can't forget the non-musical uses. This tech is used for public safety.
Absolutely. In a restaurant, the background music is compressed so you can always hear it over the chatter, even the quiet parts of a song.
And it's the absolute core of a hearing aid.
It is. A hearing aid has to take the entire dynamic range of the world and compress it into a person's specific, limited hearing range. It's a medical marvel based on compression.
There's also active hearing protection.
Right. For people at a shooting range or in a factory, the gear lets normal conversation through, but an incredibly fast limiter instantly clamps down on any loud noises like a gunshot, protecting your hearing.
So when you boil it all down, compression is just about control. Control for art, for marketing, for safety, for accessibility. Every knob is a choice.
It really is. And here's a final thought for you to experiment with. This is from a study in the Journal of the Audio Engineering Society.
Oh, this sounds interesting.
They found that while limiters, they add all that harshness, that clipped sound.
That fatiguing sound.
Exactly. But compressors that were set with a fairly slow attack time, around 50 milliseconds, they had basically no influence on that clipped sample density.
Wow. So even with the same amount of gain reduction, just changing the attack time preserves the quality of the sound.
It's the difference between controlling your dynamics and destroying your audio. It suggests that slowing down that attack knob might be one of the most important creative choices you can make to keep your sound clean and punchy.
An amazing takeaway. Think about that next time you hear a perfectly produced track. That subtle control, that punch, it's all compression shaping everything you hear. Thanks for joining us for the deep dive.